Okay, welcome back everybody. Now we have what we need to understand the origins of life, or at least to understand our understanding of the origin of life. So we want to talk about the appearance of life in the universe and what should be involved in that. We talked about the Drake equation, and the last three terms in the Drake equation are all about the creation of life, which planets actually form life, which kinds of life forms intelligence, which kinds of intelligence forms technological civilizations, and how long do those civilizations last. Now, we really can only guess about those terms, but for the first one, when does life form, we do actually have some information based on our understanding of chemistry and some experiments that we've actually done. So now, of course, what is life is kind of an open question, and you can certainly ask, is it possible to have kinds of life that maybe we wouldn't recognize as being alive? Viruses are right on the boundaries between what might be defined as being alive or not being alive. But we're going to put that aside for right now. We're just going to try and focus on life that is clearly recognizable. So, for example, what are a criterion for defining something made of life? Well, if we're going to talk about the life that we recognize, it's something that's composed of organic molecules, chains or rings of carbon or some other very chemically active element. We certainly expect there to be metabolism, right? The ability to consume energy, and of course, if you're consuming energy, thermodynamics tells us you've got to have to produce waste as well. So we expect that metabolism is going to be part of a definition of life. Reproduction, we expect that there should be more, that as time goes on, you're going to produce more of whatever you started with, right? That reproduction, the replication, maybe not exact, of, the existing beings or existing examples of life should be part of it. Mutation is very important because if you don't have mutation, you don't have the possibility of evolution. So we expect that mutation in some form should play an important role via evolution. We expect evolution to be, or we believe evolution should be a fairly universal processes. And then a sensitivity to the environment. That also ties into evolution. Because, if the environment changes, you expect that you have to respond to it or you die, right? And one of the things about mutation is that mutations will create the possibility for organisms to respond positively to their environment. If it gets drier and you have a random mutation that allows you to use water better, that you're going to tend to have your offspring make it into the next generations. Okay, so those are the basic criteria. What can we do to think about how life actually formed? Well, one amazing experiment that was done back in the 1950s, and it's been replicated many times, came from the idea of some scientists asking what were the conditions on the early Earth like, and would it be possible that those conditions could lead to the building blocks for life? So this is something that was called the Miller-Urey experiment. And basically what they did is, in a test tube, or a series of test tubes, they built a model of the early Earth. And so there was water that was being heated by geological processes, and there was material in the water that you would expect to find, all the elements that you'd expect to find in the early Earth. And they also had an electric discharge tube in there that would create lightning. And so, they basically, put all this stuff in, the water, the elements, the lightning, turned it on, and, went away for a while. They came back in a week or so, and what they found was this goo at the bottom of their test tube. And when they looked at it, they were amazed to find that basically many of the building blocks, the amino acids that are needed to form proteins, were already there. And this really gave the indication that you don't need much to sort of get the process started. Now, of course, it's a long way from amino acids to a self-replicating molecule, but of course, that long way is taken care of in some sense by time. The stretches of time over which evolution occurs are tens of millions, hundreds of millions, billions of years. And so if you have this goo at the bottom of the, of a pool of tide water, and these molecules are colliding with each other, by just, random collisions, eventually you're going to sample, you're going to start testing all the different possible configurations, and some of those configurations may eventually lead to a self-replicating molecule. And the interesting thing about that is what you then get is chemical evolution. Once you have a self-replicating molecule, then basically what it does is it eats up all the other elements or other chemicals in the pool, and it dominates. So once you can start getting self-replication, really remarkable things can begin to occur. Now, there are, difficulties with this scenario. There's things we clearly don't understand. And one of the things that that seems to be clear is that trying to go straight to DNA from, a bunch of amino acids at the bottom of a tide pool may be very difficult. And so people have begun to think about the possibilities of getting, first, there being an RNA world, that the world was full of RNA that then was an intermediary step for forming DNA. And part of that, the intermediary steps may be developing molecules that acted as autocatalysts. Now, catalyst is something that helps a chemical reaction along, speeds it up. And so if you actually had a replicating molecule that could act as its own catalyst, then you could really, drive the process much faster and produce self-replicating molecules that were more robust and that had a greater opportunity to exist in your tide pool. Now, also, tide pools may not be the only place that this could have occurred. Some people have said ice, actually, as remarkable as it may be, would be a great place to get the building blocks of life assembled, because there was water, of course, in little crevices. And also there was, the ice would act as a matrix that would, something that would hold the elements, these elements together, allowing them to interact more closely. So there's still, very many open questions, but the fundamental pieces we need for understanding how you get abiogenesis, the idea of taking non-life and turning it into life, those pieces are actually pretty solid. It really becomes sort of the mathematics of, or the statistics of how long it takes for these interactions to occur before you could sample all the possible molecules and end up with a replicator. So that's really something that is quite remarkable in our understanding of life. So, what we can see now is that, we've come to the point where we have a pretty firm understanding of how life on the Earth works. And through that, we've been able to develop at least a theoretical account for how life would begin on other planets. And one of the fascinating things that we're going to be looking for as we explore other planets, at least through telescopes over the next 20, 30, 40 years, is seeing whether we can actually get examples of other biologies. Will we see any evidence for other biologies by looking at the atmospheres of other planets? Or perhaps even within our own solar system. We have places like Mars, which certainly looked like they could have been habitable for their early parts of their existence, and maybe underground in Mars, there are places where it still is habitable, at least for bacteria. We also have things like Europa, which is one of the moons of Jupiter, which is really an ocean, essentially. It's an ocean covered by ice with a rocky core, and if there's geological activity which is creating that has thermal vents, those thermal vents are an energy source which perhaps life may have gotten a toehold there. So there may even be places in our own solar system where at least bacterial life has emerged. Now, one thing to understand about this story, or about our understanding of life, is that the Earth's record of life gives us some really interesting clues to what may have happened. For example, the Earth was formed about 4.5 billion years ago, and we have fairly good evidence that life appeared pretty quickly after the emergence, or after the planet cooled. So, by 3.8 billion years ago, or 3.4 billion years ago, we really have evidence that their life had already started. So what does that tell us? Just that one fact, sort of implies that it wasn't hard to get at least microbial life, that bacteria may be relatively easy to build. You didn't have to wait 70% of the current age of the planet for life to begin. It seemed to have appeared pretty much right after the planet appeared. So that right there is a piece of information that may indicate that that term in the Drake equation about the fraction of planets that have life, that may be, at least if we're talking microbial life, may be quite high. So that's something to remember as we go on to think about, the ultimate question is, are there other intelligent species out there that maybe someday we might be able to talk to?